Okay, it's 8:30, so let's go ahead and get started. Good morning, everybody. How's everybody doing? Did everyone enjoy their extra hour of, well, I guess for you guys, probably extra hour of studying more than sleep. But, daylight savings is here, and, at least it'll be sunnier when we start class right now. So how's everybody doing? Feeling good about the midterm, hopefully?
Still iffy.
Well, still a couple more days, so I mean, there's still time to study. Okay, so we're going to be starting something new. Good, yeah, thanks for asking. Yeah, my weekend was good. So I dropped off my ballots on Saturday, and then we visited my girlfriend's dogs at her parents' place on Saturday too. So we played with them for a while, and then came back and did some shopping. Enjoyed one more hour of sleep yesterday, and then here we are. Okay. So the plan for today is we're going to start a new unit. So the unit today is going to be called Dimensional Analysis. So this material will not be on the midterm. So basically everything that was on your study guides before, that's all you need to worry about. But this stuff will make an appearance on the final exam. Okay. And so you'll see that this is quite a bit different than what we've done. So we're not actually going to be doing explicitly any fluid mechanics. So it's kind of a weird this is kind of a weird unit. In the grand scheme of things that I think, really belongs in maybe another class, but for some reason, traditionally this unit or this topic is taught in fluid mechanics. And it's been taught in fluid mechanics basically everywhere. So, that's why, we're going to go over it. Great. Okay, good. You've seen it before, so that's good. Okay. So before we get started, are there any questions about the exam this Wednesday, or just anything I can answer before we get started?
Is the exam going to be similar like last time, where it's like we have all day to do it?
Yes. Yeah. So the exam format's going to be exactly the same. So I'm going to open up the exam at 8:30 a.m. on Wednesday, and then you're going to have 24 hours to turn the exam back in. So it's going to be on Canvas, same as before. We're going to use the in website module for quizzes on Canvas. And in terms of the breakdown for the exam, it's going to be the same too. So there's going to be 4 short answer questions. That's going to be worth 40% of the points. And then there's going to be 3 problem solving questions as well. So, format's exactly the same. It's just the topics are going to be different. Okay. All right. Any more questions before we get started?
Yeah.
Yep.
Can you remind us what W equals U minus VCV is?
W equals U minus VCV. So that's your relative velocity. So that's for a moving control volume problem. So basically what that means is that that's the velocity that you observe if you're sitting on the control volume. So, if your control volume is moving and you're kind of like sitting on top of it, the fluid velocity that you observe is not the absolute fluid velocity, but it's the difference between the fluid velocity and the control volume. So it's kind of like it's like you can imagine your control frame or your reference frame is moving.
Thanks.
Yep. Mm-hmm. Okay. All right, so let's go ahead and get started. Okay. And so the topic for this week is dimensional analysis. Okay. And so, just like I mentioned at the beginning, this is kind of like almost like a black sheep topic within fluid mechanics. It doesn't have anything directly to do with fluids, although it's used often for fluid mechanics analysis. Okay. And it's a big departure from where we've been recently, because it's not really dealing with fluid analysis, which is kind of what we've been doing. Okay. But where this really comes into play is really experimental design. And so, we'll be talking a lot about, fluid mechanics experiments in this unit, but you can apply this knowledge to almost any kind of subject, so which is nice. Okay? And, kind of begs the question of, why do we need experiments to begin with, right? Which is, kind of an obvious question, because, but, if you think about where technology has been heading nowadays, like, we've been taking this class for, 10 weeks now, and we've learned a lot of like really complicated and really complex methods and equations to analyze fluid flow. And then on the other side of that, there's also simulation technology. So if you've heard of a program called ANSYS, out there. So that's basically computer software to solve for fluid mechanics phenomena. And so, if we have all this technology, we have all these methods, there's a, I think it's a fair question to ask, and what role does experiments play, or do physical tests play, in a world where, computers are getting better, or, fluid mechanics knowledge is getting better every single day, okay? And so the answer to that is that experiments, they're kind of, you can almost think of it as like nature's best computer, okay? And so experiments are, still today the only way to prove without a doubt that something is going to happen, okay? Okay. Because as you've seen, in the past 10 weeks, even though we have like Navier-Stokes, we have, control volume analysis, we have potential flow, and you work out those problems by hand, those are subject to human errors, right? We might make an error, and that might cause, a lot of issues. And simulations are the same way. So, for simulations, there could be error, there could be bugs in the code, there could be, problems with the setup. And so the only way to get real reliable data is to just ask Mother Nature herself and to say, I have this situation. I've set up this fluid mechanics situation. Will this work? And that's basically the only thing that's really reliable. And so the other thing is that experiments really gives you a way to handle situations with really complex geometries and complex boundary conditions. Okay? And so you can see with the pen and paper methods that we've been using, we're really limited to really simple situations. But with experiments, you can really just let your imagination run wild. So as long as you can build it, you can run an experiment on it. Okay. And so the downside to using experiments, just in general, is that they're very expensive and very time-consuming to execute. Because if you can imagine, if you're working for like an aerospace company like Lockheed or something, or Boeing, and you want to run an experiment on how well like a rocket ship wing will hold up as it exits the atmosphere, right? And so if you run an experiment on that, you got to build the entire rocket wing. You got to build the experimental setup. You have to make the conditions just right, and all this is extremely expensive, and usually it'll take months to do. Okay, and so when you do want to run experiments in professional engineering work, you really want to make sure that it's worth it. Okay, or in other words, you really want to make sure that the experiments and the data that you collect can be applicable and can be applied to a lot of different situations. Okay, or in other words, we want to design our experiment we want to design our experiments and analyze the data in order to get the most out of it as possible. Right. And so to help this with experimental design and with the data analysis, we have this this topic of dimensional analysis, which will basically allow us to analyze the data and put things in terms of these things called dimensionless variables or dimensionless numbers, and that really helps with the analysis and the experimental design. Okay. And so one other thing that we'll go over at the end of the week, or probably next week, because we're taking the midterm this week, is this idea of similitude. And what similitude will allow us to do is that it'll allow us to basically scale our experiments down, to make much cheaper experiments. So instead of building a huge, a full-size airplane wing, you can maybe do it on a much smaller scale, and still get really useful information out of it. Okay. Okay. Any questions on this so far? Okay. Okay, so the whole driving force behind this this unit is a theorem called Buckingham-Pi. Okay. And his whole thing was built around this idea of what's called dimensionless groups. Okay. And so the whole idea behind Buckingham-Pi dimensionless groups and actually just fluid mechanics situations in general is that we're usually solving for some variable of interest. Okay. Okay. So if you think back to our last unit on Navier-Stokes, then that variable of interest would be like the velocity field or the velocity distribution. Oh yeah, sure, I can go back a page. Okay. Okay. And so when we solve for these problems, this variable of interest, like the velocity field or like a pressure or something, this is often a function of the other physical parameters in the system. Okay. And so if you think of like like Navier-Stokes, so we're solving for the velocity, and that's a function of the viscosity, that's a function of gravity, it's a function of the pressure gradient and stuff like that. Okay. And so as kind of an example, and we're going to be working with this example, throughout the lecture today. Let's consider a flow in a pipe. Okay. Right. And let's say on one side of the pipe we have P1, and we have another side of the pipe we have P2. Okay. And so if we define the pressure drop along this pipe as P1 minus P2, okay, let's say that this pressure drop is our variable of interest. Okay. And so this pressure drop is going to be a function of the other parameters in the system. Okay. And so some of these parameters are going to be and so some of these other parameters could be one, like the pipe diameter. Okay, so we'll call that D. Two could be like the fluid density. Okay. And so we'll give that the symbol rho. Three is going to be the fluid viscosity. Okay. And so viscosity will give the symbol mu. Okay. And finally, we have the fluid velocity. Okay. Which we'll call V. Okay. And so the way that we can express that is, we can say that this pressure drop will depend on these four, physical variables. Okay. And so mathematically, we can express it like this. So we can say that delta P is equal to a function of D, rho, mu, and V. Okay. Right. And so what we're saying is that, if we change the diameter, so we make the pipe bigger or something, that's going to change the pressure drop in our system. If we exchange the fluid for something else, we change the density or the viscosity, that's also going to change the pressure drop. And if we flow the fluid at a higher speed or a lower speed, this is also going to affect the pressure drop as well. Okay. And so this mathematical expression just basically says that our variable of interest will depend on these other guys. Okay. And so the key thing right here is this F. Okay? And so what this F basically expresses is that the pressure drop is a function of. Okay? Function of or depends on. Okay? Okay. Any questions on this? Okay. Okay. So if we have this relationship right here, and we say that we want to run an experiment to measure this pressure drop, the way that the situation is right now is that it's really difficult to run the experiment. Okay. Because if we wanted to see, if we wanted to test every single combination, we would do experiments with pipes of different diameters. So we might do 5 different diameters. We might do 5 different kinds of fluids, and we might do 5 different kinds of speeds, just to kind of throw some numbers in there. Okay. But if you change each of these individually, it would take a really long time because, for each pipe diameter, you have to test for each fluid for each velocity. Okay. And so if you have 5, 5, and 5, right? So 5 different pipes, 5 different fluids, 5 different velocities. That's 125 trials right there. So that's 5 cubed. And so that's kind of crazy. So that's a lot of tests to run just to just to measure something simple like a pressure drop. Okay. And the worst thing is that if you run an experiment like this, it would only be applicable to this kind of pipe and this kind of fluid. So we wouldn't be able to generalize these results at all. Okay. And so a better way to run this experiment is to do it in terms of dimensionless groups. Okay. All right. So the question there's a question in the chat that says, is dynamic viscosity the only viscosity that affects this, and what about kinematic viscosity? Yeah, that's a good question. So it's in this particular case, and we'll touch back on this later. You can either do dynamic viscosity or kinematic viscosity, and so those two variables are related, obviously. So you need both of them. So it will be affected on both of them. But you can see here we have density and dynamic viscosity, and so the kinematic viscosity can be found by a combination of the other ones. But and so the variables that you pick, kind of in these parentheses here, have to be, we call them independent. But we'll touch back on this a bit later. Okay. Yep. Okay. And so a better way to approach this experiment, instead of doing all these things individually, is to put them in terms of dimensionless groups. Okay. And so we've seen dimensionless groups before, or you saw it briefly on the first midterm. Okay. And so dimensionless groups are basically groups of variables that are combined in such a way that they're dimensionless. Okay. And so for this particular problem, a dimensionless group would be the diameter multiplied by the pressure drop divided by rho v squared, okay, is equal to a function of, so this phi right here is another function of. And so the phi is not a variable in itself, it's just a function of something. Okay, it's equal to rho v d over mu. Okay, right. And so if we do the experiment in terms of this, you can see we have a lot less variables, right? So on the left hand side we have our dependent variable, and on the right hand side we have our independent variable. Okay, and so instead of having what we have here, we had 1, 2, 3, 4, 5. Instead of 5 variables, now we have only 2, which is really good. Okay. And so what's special about this expression is that both of these guys in the boxes, these guys are dimensionless. Okay. Okay. And so if you actually wrote out the dimensions for each of these guys, you did everything in terms of mass, length, and time. or force length and time, you can see that all the dimensions are going to cancel out. Okay. And so if we design our experiment and instead of varying each of the variables, independently, if we instead vary this quantity right here systematically, we're going to cut down the amount of work that we're going to do, really, really significantly. Okay. Not only that, what's going to happen is that if we run this experiment in terms of this dimensionless variable, we can extend these simulation results, or we can extend these experimental results to any kind of pipe, as long as they have the same dimensionless variables that we have here in this experiment. Okay. And so it doesn't matter what fluid you have or how big the pipe is, as long as you express the results in terms of this, then this results will be applicable to anything. So obviously this is really desirable, because this saves us not only a ton of work up front to do the experiment, but for any kinds of pipe or any kinds of pipe that we're interested in measuring the pressure drop for, we've already kind of done the work for that. Okay? And so now the question becomes, if these dimensionless groups are so great, how do we even obtain these groups? Okay? And so that's going to be the subject for most of this week, was how do we actually obtain these guys? Okay, and so to do that we need a new theorem, and that's going to be the Buckingham-Pi theorem, which is the title of this section. Okay. And so I'm going to write out the kind of the definition of Buckingham-Pi, and then we'll kind of walk through the entire method and how to use it. Okay. And so Buckingham-Pi states this: so if an equation and let's say this equation involves k variables, okay, where k here is some integer, so it's just some number, okay, and we say that this equation is dimensionally homogeneous, okay. If this is the case, okay, then we can reduce the relationship among k minus r dimensionless products. Okay. Okay. Where r here is another number, and r represents the minimum number of reference dimensions. Okay, and so that's the formal declaration of Buckingham-Pi. So I know it's a little bit things aren't really well defined yet, so we'll kind of go into it in a bit. Okay, but it's just but from this page, the most important thing is I want you to get that for any kind of experiment or any kind of relationship, we can express it in terms of these dimensionless variables up here. Okay, so are there any questions on that before I turn the page? Okay. And so the most important things in Buckingham-Pi are the two numbers, okay? And so K right here, K is is basically the number of variables in our system. Okay? And so if we go back to our pressure drop example, so we'll say we had delta P is equal to F function of D, rho, mu, and V, okay? And so in order to get K, all we have to do is just count out the variables. We have 1, 2, 3, 4, 5, okay? So the F is not a variable, F just expresses function of, okay? And so in this particular case, K is equal to 5, okay? Right. Okay. And so K is relatively simple, okay? And so R, remember R right here is the number of reference dimensions. Okay. Right. And so what R represents is the number of basic dimensions that's represented in our equations. Okay. Okay. And so let's recall basically our basic dimensions. So we had this kind of goes back to week 1. Okay. Okay. And so we had two systems of basic dimensions. We had MLT, which is mass, length, and time. Okay. And we also had FLT, which is force, length, and time. Okay. And so you can use either one of these, but don't use both, okay? And so R basically is going to be a number between 1 and 3, okay? Okay. Where the number is going to represent how many of these basic dimensions are represented in our variables, okay? And so if we look at our variables right here, we can we need to check to see, you know, if mass, length, how many between mass, length, and time are represented, okay? And so I'll tell you right now, just as a pro tip, most of the time for fluid mechanics problems, R is going to equal to 3, okay? Because of the way fluid mechanics problems are, you know, most of the time you're going to have mass, length, and time. All of them are going to be represented into your equations, okay? And so just as an example, let's take V, okay? And so V, the dimensions for that are going to be length over time because it's the velocity, okay? And so from this, we have length and time represented. Okay. And then let's also look at the density, okay? And so density is going to be mass over length cubed, okay? So this is mass and length, okay? And so from these expressions, we can see that length is represented. It's actually represented in 2 places, okay? Time is represented, and also mass, okay? And so since all 3 of mass, length, and time are at least represented at least once in our variables, we say that R is equal to 3 in this case, okay? Okay? So those are the definitions of K and R, okay? Are there any questions on this?
Are we to classify the numbers of R's?
Say it
Or
again.
not? Are we to classify the how many what the value of R is, or no?
Yeah, so the value of R is going to be determined from your variable list. And so you'll see kind of when we do these problems, actually the hardest thing to do, you know, for just a general kind of fluid mechanics experiment or just any experiment is to determine, you know, what variables are there. And then once you have the variable list, then you look at the dimensions of each of the variables, and then you see how many of the basic dimensions are represented. But the hardest thing actually is to get K, because you know for everything in this class, I'm going to give you the list of the variables, but in general, it's normally difficult to determine what that is. But then once you have the list of variables, then determining R is usually pretty simple. 99% of the time, R is going to be 3 because, you know, if you have a situation where it's worth doing an experiment on, usually it's pretty complex. It's going to involve mass, length, and time. So most of the times it's going to be 3, but there might be some situations where, you know, it's not the case.
Okay. Thanks.
Right. Any other questions on this? Okay. And so once you've determined K and R from your, you know, for your variable list, then all you have to do here is to just take the difference between them. Okay. And so that's where Buckingham-Pi actually comes in. Okay. And so Buckingham-Pi basically tells you the number of dimensionless groups that your situation is going to rely on. Okay. And so Buckingham-Pi lets you compute number of dimensionless groups. And so it's actually pretty simple. So once you have K and once you have R, all you have to do is subtract them. Okay. Okay. So that's all Buckingham-Pi. So Buckingham-Pi is just K minus R. So the hard thing is actually, you know, determining K and determining R. And so in this particular, you know, example that we're doing, you know, we have 5 variables and our R is 3. And so this is going to give us 2 dimensionless groups. Okay. Right. And so since, you know, this whole idea of you know, Buckingham-Pi came from this guy, you know, we often call these dimensionless groups pi terms. Right. Okay. Or literally, you know, the symbol pi. Okay. And so if you see the term pi terms, or dimensionless groups, they all mean the same thing. I will admit that writing out pi terms is a lot shorter than writing out dimensionless groups, but I think dimensionless groups describes what it is a lot simpler. Okay. And so if you're curious, you know, the guy who invented this theorem, his name was Edgar Buckingham, and I guess he just liked the symbol pi, so that's, you know, that's why he chose that. Probably he was British or something. I don't know. I looked it up on Wikipedia just for this because it's I know people are curious. Okay. So that's how we determine the number of pi terms, but we haven't talked about how we actually determine what those pi terms are. Okay. And so the next section is going to be the derivation of pi terms. Okay. And so the method that we're going to use for this is called the method of repeating variables. Okay. And that we're going to spend the rest of the class today kind of you know, discussing this. Okay. And so it's basically it's an 8-step process. So it seems like a lot of steps, but the later steps are not that bad. Okay. And so to kind of illustrate it in action, we're going to continue on with this example of the pressure drop in a pipe. Okay. Okay. Any questions on this before we start going over this method of repeating variables? Okay. Okay. And so I'm going to list these basically as like step 1, step 2, step 3, and so forth. Okay? So step 1. Okay. And so step 1 is literally just to list out all the relevant variables. Okay. Okay. And so I know this is just step 1, but step 1 is actually, you know, the most difficult part of this entire thing. Okay. Which, you know, for this class, you know, I'm unfortunately going to be robbing you of the fun of doing step 1 because, you know, just to make sure that everyone gets, you know, can do these problems, I'm usually going to give you the list of the variables. Okay. But I really want to spend some time talking about how you would do this in practice because, you know, this is a really useful technique for doing experiments, you know, not only fluid mechanics, but also in other ones. Okay. Okay. And so the starting point for step 1 is to first list out what is your variable of interest. Okay. Okay. Or basically, you know, why are you running this experiment to begin with? You know, what are you interested in solving for? Okay. And so, you know, because this is our, you know, the variable that we want to test for, another name for this, which you've probably used in previous lab classes, that this is our dependent variable. Okay. And so in this particular case, you know, for our example, you know, our variable of interest here is our pressure drop. Okay. And so, you know, that's always going to be one of your variables. So that's a good place to start. Okay. And so from here, you know, what we need to do is we need to list out all the variables that will affect our dependent variable. Right? And so this is the part that's hard, especially you know, if you're just learning kind of a new subject, it's really hard to get that kind of perspective and you know the to know, you know, what things will affect each other. Okay. If you've been doing, you know, fluid mechanics for a lot of years, you know, this is you know, it becomes easier just because you have a much, you know, wider breadth of knowledge of, you know, what are all the equations, and you know, you've seen some kind of experiments. Okay. But when you're first starting out, this is usually pretty hard. Okay. And so what I want to give you is just some kind of you know, some tips on how you can do this. Okay. And so some places that you can check. And so the first thing that you can check is just the geometry of your system. Okay. And so most of the time, you know, the geometry is going to have some kind of effect on your results. Okay. And so most of the times this takes the form of some kind of lengths. Okay. That characterize your system. And so in this example, you know, we have our pipe. And so one geometry characteristic that can determine that is the diameter of the pipe. Okay. And so, you know, the first step I would say to look at, you know, when you're doing this method of repeating variables is to look at the geometry of your system and see, you know, what variables are there in this geometry that can be used to describe it. Okay. So most of the time it's going to be some kind of diameter, some kind of length, maybe some kind of area. And so you know, listing those things out is usually a good place to start because these usually have a big impact on the results. Okay. All right. And so the second thing is fluid properties. Okay. And so things like viscosity, things like density, things like velocity, pressure, right? In this case, we're solving for pressure, but if we're solving for something else, you know, it would go into this category right here. So, you know, basically what the question is, you can ask is, if I change this fluid to something else, if I change this water to air, if I change this water to motor oil, is that going to affect the result? So most of the time, the answer is going to be yes. Okay. Okay. All right. And then number three, number three is just any kind of external effects or external forcing. Okay. And so, if you apply kind of an external force, either from like a pump or something like that, or there's a turbine or something like that, then that's also going to, affect your results as well. Okay. And so these are some kind of, these are generally the three categories of variables that you will put into your Buckingham-Pi. But there might be some other ones that don't fit these categories too. So the important thing is to always kind of be observant and just kind of ask yourself, what if I change something in my system, how is that going to change my dependent variable? And if you can find something that if you change this, then it's going to change, and it's going to affect our results. That's something that you should put into your system. Okay. Right. And so another tip that I'll give you for this is to, if you're kind of stuck or if you're not sure that you got all the variables, is to look at the governing equations. Okay? Okay. And so, this will be things like Navier-Stokes or Bernoulli. Okay. And so, you don't have to solve these equations because if you could solve them, then there's no point in doing the experiment. But, what I want you to look at is to look at these equations and see what variables are in these equations. And those are usually some good ones to include into your list of variables for step one. Okay. Right. So step one, remember, step one is usually the hardest case, but, it really pays to really take your time with this and to really think, both inside the box of, what are some of the most obvious things that can affect your results, but also, maybe outside the box as well. Okay. Okay. Any questions on this? Okay. Okay. And so another important feature of step one is that all your variables need to be independent. Right, so they don't need no strong, other variables to depend on. Okay. Okay, and so what this basically means is that all the variables in your list, there should be no other way to obtain those variables. Okay, from the other variables. Okay. So there should be no other way to obtain a variable in your list through a simple combination of the other variables. Okay. Right. And so, for example, for this example right here, we already have the diameter. Okay. Okay. And so the diameter here is independent. Okay. And so what can't happen is that if we have the diameter and also the radius. Okay. Okay. And so we can't have both diameter and radius in our list, because how do we obtain radius? Okay. Because radius can be obtained by just taking diameter divided by 2. Okay. And so in this case, there's no point at all to have radius because, radius is just, diameter divided by 2. And so the same thing is for area, right? And so we can't have both diameter and area, right? Because area, the way that we obtain that is just pi over 4 diameter squared, okay? And so we can't have, both these at the same time, okay? Right? And so what you could have is that instead of diameter, you could have radius, and that's fine because radius by itself is independent, but we can't have 2 variables here that are, that are not independent, okay? And so when you're choosing the variables, don't kind of double count, some variables like this, okay? All right. And so for diameter, this is pretty simple because, there's just kind of a simple relationship. But another one that might not be so simple is, is actually the point that Danny brought up, which is some variables might be dependent according to other stuff, okay? Right. And so let's look at kinematic viscosity, okay? And so kinematic viscosity is given the simple nu, which is kind of this squiggly v, okay? And then the formula for nu is going to be our dynamic viscosity divided by density, okay? And so in this particular case, the kinematic viscosity is non-independent, okay? Because what do we already have in our variable list? So we already have, dynamic viscosity, okay? And we also have density in our list already, okay? And so since we have the dynamic viscosity and the density in our list already, including the kinematic viscosity here would be redundant because we can obtain the kinematic viscosity just by taking dynamic viscosity divided by the density, okay? And so in this particular case, dynamic viscosity and density are independent of each other, but because we have those in the list already, then kinematic viscosity would not be there, okay? Right? And so this, as you can imagine, for a new situation, this can be, a little bit difficult to obtain. So, it's, making sure your variables are independent is a really important step because otherwise this method is not going to work. But you really need to look at kind of all different combinations of your variables to make sure that they're all independent. Okay. Okay. Any questions on this? Okay. Okay. And so just to summarize, let me write out the full list of variables that we have, and let me categorize them as, the different things that we had before. Okay. So first we had our pressure drop. Okay. And so this pressure drop, remember, was our dependent variable. Okay. And so since it's a dependent variable, it's automatically added to the list. Okay. Okay. Next we had our diameter. And so diameter here, this was a geometrical parameter. Okay. Okay. Next we have the density. Okay. So the density here is a fluid property. Okay. Next we have our viscosity, dynamic viscosity. Okay. This is also a fluid property. And then finally, we have the velocity, and this is also a fluid property. And so these are the 5 variables that we're going to be working with, for the rest of this example. Okay. Okay. All right. So that's step 1. So remember, step 1 is usually the hardest, but for this class, I'm usually just going to give you step 1. Okay. Okay. Step 2. Step 1 is also the longest, so all the other steps will be shorter than this. Okay. And so step 2 is basically to take all your variables and express them in terms of basic dimensions. Okay. Okay. And so what this basically means is we're going to take this back to kind of the first week of class where we express variables in terms of mass, length, and time, or force, length, and time. Okay. So remember, you can use either one, but for in this for this example, and the one that I personally like to use is I like to use mass, length, and time. Okay. Okay. So let's go ahead and do that. Right. Right. So let's look at pressure drop. And so pressure drop is a combination of force over an area. Okay. And so force, the dimensions for that is mass, length over time squared. Okay. And then area has dimensions of length squared. Okay. And so the dimensions for this is going to be mass over length times squared. Okay. And so that's the dimensions for pressure. Okay. The dimensions for diameter are just going to be length. Okay. Right. Next we have density. And so density is a mass over length cubed. Okay. Right. The dimensions for dynamic viscosity is going to be mass over length time. Okay. Okay. And then finally, the dimensions for velocity is going to be length over time. Okay. Right. So step two, once you have step one down, step two is relatively simple because you're just going to basically look up the variables in the, there was a big table that I had in kind of the first set of lecture notes, and then just express these variables in terms of their basic dimensions. Okay. And so basically in terms of mass, length, and time, or force, length. Okay. Any questions on this? Okay. Great. And so once you've done step two, step three is to determine the number of pi terms. Okay. Or in other words, determine the number of dimensionless groups. Okay. Okay. And remember to do this, we're going to do Buckingham-Pi. Okay. And so all we're going to do is just simply take the difference between K and R. Okay. And so for this particular problem, K is 5, R is 3 for the reasons that we've listed above. Okay. And so for this, we have 2 pi terms. Okay. I see there's a question in the chat. Okay. Oh, sure. I can go back. All right. Are you good? Cool. Okay. And so, step three is relatively simple because you did, all the work in step one and step two. Then all you got to do is just take the difference between K and R. Okay? Where remember, K is the number of variables that you have, and R is the number of basic dimensions that are represented. Okay. Okay. And so step four is going to be another tough one. And so in step four, we have to choose which variables will be repeating. Okay. Okay. And so basically what we'll see is that in order to form dimensionless groups, it's going to be necessary for some of these variables to participate in multiple groups. Okay. Okay. And so the variables that participate in multiple groups, these are known as the repeating variables, okay? And so there's some criteria that these repeating variables need to have. Okay? Okay. Okay. And so the first criteria is just the number of them, okay? And so the number of repeating variables is going to be equal to R, okay? Okay. And so most of the time it's going to be 3, okay? Okay. Another criteria that these repeating variables need to have is that as a group, all 3 of them, they need to represent all the basic dimensions. Okay. Okay. And so that's not individually. So that basically means as a group, we need to have at least one mass, we need to have one length, and we have at least one time. Okay. Number 3 is not a requirement, but it'll make your life a lot easier. And so the repeating variable should also be as simple as possible. Okay. Okay. And so you shouldn't choose variables with a ton of stuff going on, because that's going to make your life miserable. Okay. And so the last requirement is that your dependent variable cannot be a repeating variable. Okay. And so those are the 4 criteria that we're going to do. All right, any questions on this? Okay. Okay, and so for our example here, we're going to choose these repeating variables. Okay. And so first, let's choose the diameter. Okay. And so if you have a diameter, this is usually a really nice one, just because it's it's really simple, because the dimensions for diameter are just length. Okay. Right. So that takes care of length, and so we need one guy to represent mass now. Okay. Okay. And so the simplest term here that actually has mass is our density. Okay. And so density is just going to be mass over length cubed. And so not as simple with diameter, but it's still only 2 guys. So that's good. Right. So that takes care of mass. That takes care of length. Okay. And so the only thing else we need is we need one term that represents time. Okay. And so the simplest variable that has time in our system is velocity, which is length over time. Okay. All right. So that's step 4. Okay, is to choose the repeating variables. Okay. And so now that we have the repeating variables, just by process of elimination, our remaining 2 variables are going to be non-repeating. Okay? And then from those non-repeating variables, we're going to form our pi terms. Okay. And so for each of the variables that are left, okay, we're going to form a dimensionless group. Okay. Okay. And the way we're going to do that is we're going to multiply these by our repeating variables. Okay. Okay, and so let's do that for this example. Okay. And so our first dimensionless group, we'll call it pi1, is going to be the product between the pressure drop. Okay, and so that's our dependent variable. Okay. Then we're going to multiply by the diameter. Then we're going to multiply by the density. And then we're also going to multiply by velocity. Okay. And so what we're going to do, just to make sure this is dimensionless, is we're going to apply exponents to these. Okay. Right, so we're going to apply an exponent of A1 on the diameter, an exponent of B1 on the density, and an exponent of C1 on the velocity. Okay. Right, so that's the first pi term. And the next pi term is going to be our other non-repeating variable, which in this case was the viscosity. Okay. Okay. And same thing, we're going to multiply this by our repeating variables, and we're going to raise them to some exponent. Okay. Right. And so what we need to do at this point is we need to solve for the exponents that make each of these pi terms dimensionless. Okay. And so the way that we're going to do this is we're going to form, we're going to basically plug in the basic dimensions, and then we're going to solve a 3 by 3 linear system, okay, for A, B, and C. Okay. All right, so I'll do that on the next page. But before I get there, are there any questions on this? Okay. Okay, so let's do pi1. Okay. So remember, pi1 was the product of our pressure drop, our diameter, and density and velocity. Okay, and so let's plug in the dimensions for all of these guys. Okay? And so the dimensions for pressure are going to be mass over length times time squared. Okay. Then we have our diameter. So our diameter has dimensions of length. Okay? And we're going to raise this to the A1 power. Next, we have our density, which has dimensions of mass over length cubed. Okay? And we're going to raise this to the B1 power. And then finally, we have the dimensions of velocity, which is length over time. Okay? And then we're going to raise this to the C1 power. Okay? And so just to kind of remind you, this is dimensions for delta P. This is dimensions for diameter. This is dimensions for density. And this is the dimensions for velocity. Okay, and so now what we need to do is we need to form a 3-equation, 3 unknown linear system okay, to basically solve for A1, B1, and C1. Okay. Okay, and so the way that we're going to do this is we're going to make one equation for each dimension. Okay. Okay. And so we're going to have a mass equation. We're going to have a length equation. We're also going to have a time equation. Okay. And so the way we're going to do this is we're going to look across on the system, and every time that there's a mass term, we're going to put it into this equation. Okay. And so the first thing that we have is we have a mass term from the pressure. Okay. And so the mass is in the numerator, and it has a exponent of 1. And so we have a 1 right here. Okay. And then the other time that mass shows up is in the density term. Okay. And so you can see here that m is in the numerator, so it has a coefficient of 1. But we're also raising this entire expression to the B1 power. Okay. Okay. And so the mass equation is just going to be 1 plus B1, and this is going to be equal to 0. Okay. All right. Does that make sense how we got that equation from the exponents here? Okay. Okay. And so that's the mass equation. So now let's write out the length equation. Okay. And so for lengths, we can see that we have a -1 from the pressure because we have a length in the denominator. Okay. Plus a positive A1, so the A1 comes from the diameter. Okay. And then we have a -3 B1 because for the density term we have L cubed in the denominator. Okay. And then we also have a C1 that comes from the velocity. Okay. And so length is pretty crowded. So length involves all 3 variables. Okay. Okay. And then finally for time, we can see that we have a -2 that comes from the pressure term because we have t squared on the denominator there. And then we have a -C1 because we have a time in the denominator for our velocity term. Okay. Okay. And then from here, we can solve for all of our exponents. Okay. And so from this first equation, we simply get b is equal to -1. And from the last equation, we get C1 is equal to -2. Okay. And then once we solve for B1 and C1, we can plug that into the middle equation and solve for A1. Okay. And then from here, we get that A1 is equal to 0. Okay. Right. And so now that we have these, we can form our first pi term. Okay. Right? And so does it make sense, why we set all these equations equal to 0, right? Because we set them equal to 0 because we want these pi terms to be dimensionless, okay? And so if it's dimensionless, that means it has no dimensions at all, okay? Right. And so once we do that, we can basically plug these values in, and then what we get is pi1 is equal to delta p divided by, A1 is 0, so there's going to be no diameter here, okay? And so B1 is -1, so we have a density in the diameter, okay? Or in the denominator, and then we also have a C1 is equal to -2, and so we have velocity squared, okay? And so there's our first pi term that we just obtained from this, okay? All right, any questions on this? Okay. So that's the first pi term. So let's now form the second one. Okay. Okay. And so our second term, we have density here. So that's going to be, or viscosity, sorry. And so that's going to be m over L times t. Okay. Then we have our diameter, which is length. Okay. And this is raised to the A2 power. Then we have our density, which is mass over length cubed. Okay, and this is raised to the B2 power. Okay, and then we have our velocity, which is raised to the C2 power. Okay, and so just like we did before, we're going to form our linear system. Okay, okay, and so for the mass terms, we're going to have 1 plus B2 is equal to 0. Okay, and so from this, we can see that B2 right away is going to be -1. Okay. And so for lengths, we have -1 plus A2 minus 3B2 plus C2. All that's equal to 0. Okay. Okay. And then for the last equation, we have time. We have -1 minus C2 is equal to 0. We get that C2 is equal to -1. Okay. We plug this into the middle equation, and what we get is A2 is equal to -1. And so our second pi term here is going to be viscosity divided by everything to the -1 power. So we have diameter, we have density, and we have velocity. Okay. Okay. So that's our second pi term. Okay. And so that's step 5. So step 5 is, also kind of another big one because you have to solve these linear systems. Okay. And so once you're done with step 5, then there's going to be step 6. Okay. And so step 6 is simply just going to be to verify each term is dimensionless. Okay. And so step 6, we're basically just going to be checking our work. So, you know, it's always a good practice to check your work. Okay. And so in this particular case, you know, since this is the example, you know, we know that they're all dimensionless, but, you know, once you're, when you're doing your problems, you know, make sure that you, you actually check them. Okay. All right. Any questions on this? Okay. Okay. And so once you're done with that, then it's, then you're basically done. Okay. So I might have said earlier that it's an 8-step process, but it's actually a 7-step process. Okay? And so step 7 is to basically just form the final relationship. Okay. And so the way that we're going to do this is we're going to put our dependent variable or dependent pi term on the side. Okay. On the left hand side. Okay. It's going to be equal to some function. So remember, phi right here represents some function. Okay. Okay. It's going to be some function of the independent pi terms. Okay. And so for this particular case, our dependent pi term is going to be our pressure drop divided by the density times velocity squared. Okay. It's going to be some function of mu divided by diameter rho times velocity. Okay. And so remember that this phi right here represents some relationship. Okay. Right. And so what we say is that this product right here of the pressure drop divided by the density times the velocity squared is dependent on this dimensionless parameter of the viscosity divided by the diameter times density times velocity. Okay. And so we don't know what that relationship is. So it's like, you know, high school drama. So we say that it's complicated. But the way that we usually find this relationship is to run our experiments. Okay. Don't do that in real life. So don't test your relationship with other people running experiments because nobody likes that. Okay. All right. And, any questions on this? Okay. Yep. Go ahead.
Professor, can you hear me?
Yep. Mm-hmm.
Can you go back to the previous page?
Sure.
For the pi 2 equation right there, does it have to be in that specific order?
It doesn't have to be, no, but it's because you just need to solve for the exponents a2, b2, and c2. So you can list the variables in whatever order that you want, as long as the exponents that you solve for are consistent.
All right, thanks.
Mm-hmm. All right. Any other questions? Okay, so that's all we got time for today. And so when we pick this up next Monday, we're going to do another example just to kind of illustrate this whole process to you. Because I know today, you know, we were learning the process and kind of doing the example at the same time. And so I think it'd be useful next time to do just an example from scratch, just so you can see that the process in action again. Okay. And so Wednesday is going to be our midterm. So just like last time, I'm going to open up a Zoom call if you want to ask questions. But you know, but you don't have to come. So basically, on Wednesday, you just have to take your midterm and then just make sure you turn it in before the 24-hour deadline. Okay. right, so best of luck studying for the exam, everyone. If you have any more questions, I have office hours after at 10 o'clock today, and then office hours tomorrow at 2:30. So you can stop by. But otherwise, you can send me an email or message me on Discord, and I'm happy to answer. Okay? All right, so best of luck studying. If I see you Wednesday, I see you Wednesday. But if not, I'll see you next week. So thank you, everybody, and have a good day.
Thank you, Professor. Take it easy.
Thanks. You too.
Thanks, Professor.
Thanks, Stephen. Did you guys have any other questions? Okay. So if there's no more questions, I'm going to close the call. But if you have any more questions, I have office hours soon, so you guys can stop by.